Good day, welcome back, ladies and gentlemen. Today we will be applying some calculus. Our first example has to do with something called kinematics, which is the study of how object moves. And we're going to start very simply. We're going to be looking at a particle moving in a straight line. Once we add curved trajectories, this becomes a bit more complex. We're going to stick with a single one-dimensional motion just going back and forth on this line. So this particle has its position on a line modeled by the function t cubed minus 7t squared plus 11t minus 2.5. We want to do these four things that are listed on your screen. Find the velocity and acceleration at any time t. That means find a function for velocity and acceleration. B, find the times the particle is at rest, speeding up and slowing down. Find when the direction changes, and find the total distance traveled in 3 seconds. So, let's start with part A. Find the velocity and acceleration. So velocity is the derivative of the position function. And we know how to find the derivative of that, but just so that you're trying a little bit here, pause the video, differentiate s of t. So you should have gotten 3t squared minus 14t plus 11. And now we also want the acceleration. Well, that's the second derivative of position function. So here we have 6t minus 14. Cool. Awesome. Good to go. Part A in the books. So for part B, how do we know when the particle is at rest? Well, that's when the velocity is 0. Okay, so let's take v of t and set it equal to 0. And we have this quadratic. And you know what? I'm going to sort of assume for a minute that you all know how to solve quadratic equations and know that you can get to t equals 1 or t equals 11 over 3. So this is where the particle is at rest. We want to know when it's speeding up and slowing down. So here's what we're going to do. We're going to make a sign diagram for the velocity. The velocity is equal to 0 at 1 and 11/3. For t values less than 1, v of t is positive. For t values between 1 and 11/3, v of t is negative. And for t values greater than 11/3, our velocity is positive again. So does this tell me what I need to know? Absolutely not. This does not tell me whatsoever when I'm speeding up and slowing down. This is telling me that over here, we are moving to the right, moving to the left, and then moving to the right again. That's all it tells me. In order to know when we're speeding up and slowing down, we need to look at the acceleration. And what we're looking for is when the direction of the acceleration is opposite the direction of travel. We want the direction of travel, the velocity, to be positive and the acceleration to be negative, or vice versa. So let's set the second derivative equal to 0. We get t equals 7/3. So I'm going to make a sign diagram right underneath this with roughly the same scale. When we pick a value of t that's smaller than 7/3, we get an acceleration that is less than 0. When we use a value of t that's greater than 7/3, we get an acceleration that is greater than 0. So when are we slowing down? Remember, we're looking for where the acceleration and velocity have different signs. So that occurs in this part and in that part. In the unhighlighted parts, the acceleration is in the same direction as the velocity, meaning that we're speeding up for those points in time. So putting this into interval notation, we are speeding up for the intervals where t is between 1 and 7/3 and t is bigger than 11/3, and we are slowing down when t is less than 1, greater than 0, of course. Remember, there's technically time equals 0 over here where we're starting, and t is between 7/3 and 11/3. Part C, find the values of t when the direction changes. Well, we have that from our velocity sign diagram. Our velocity sign diagram says we change directions at t equals 1 and t equals 11/3. That's where we switch from traveling to the left to the right and vice versa. Now for part D, find the total distance traveled in 3 directions, in 3 seconds. So what you need to do here is you should picture that this particle is traveling to the left and then turns around and comes back, and then at 3 2/3 seconds it turns around again, but I only want to go to 3 seconds. Here's 0. So what we need to do is we need to look at the distance traveled in both of these legs, in both of these pieces of this particle's trip. So how far does it travel in the first second? How far does it travel between t equals 0 and t equals 1 when it changes direction? Well, that's easy enough to find out. We can find s of 1 and subtract s of 0. And what we get is 5. Plugging 1 and 0 into our position function because I'm looking for distance. And then how far does it travel between t equals 1 and t equals 3 over here? So we're doing S3, the position at 3 seconds, minus the position at 1 second. And what we find is that that's -8. Well, why are these different signs? That's because we're moving. You gotta remember this is directional. So we move 5 units to the right and then 8 to the left. So that means we travel a total distance of 13 meters. And there we go. There is an application of calculus involving motion of a particle on a straight line.